Yeah. It's not going to take too long, I think. So. All right. Let's talk about some of the reactions that are taking place here in this analysis. And so, if we look at the test for silver ion, this is the way we want to break down the analysis. This is the way we want to understand, because you really should, it's not just this cookbook procedure, but you really should understand the reactions that are taking place. That way you can interpret things. And sometimes the interpretation is very difficult because, colors don't look the same, this doesn't look the same, that doesn't look the same. But what you can do is you can narrow it down, because if you know what kinds of reactions take place, then you can see, what types of interferences could potentially be possible here, and that could help you analyze your unknown if something doesn't happen, for example. And so, in the test for silver, what we do is we take our unknown solution. Maybe I'll dash the solutions, and so your unknown, contains silver, maybe not. But if it contains silver, what we have is, when we add what? Hydrochloric acid, we should get silver chloride PPT. White PPT, solid. All right, this is your flow chart. You can basically see everything in your flow chart. And what I wanted you guys to do is to write the reactions next to it. And so we're going to have a little different organization here for this, etc. Let me erase this, because the observation is if you take your unknown AQ plus HCl, we should get a white PPT. And the reaction that goes with this observation is your unknown should contain silver ion if you get a precipitate here, and that reacts with the chloride ion. We get AgCl. This is a metathesis reaction. Right. Okay, then what did you do? Well, you separated out the PPT, right? And so what we do is we take the PPT from 1 and then add excess ammonia to this, and we get a CCS. A clear colorless solution. In other words, the PPT dissolves. Right? And so what's the reaction for this? Well, the reaction for this is silver chloride solid plus excess ammonia is going to yield the diamine silver ion and chloride. And then you added some nitric acid to this, right? So what we did was we took the CCS from part 2 and then add some nitric acid to that, and then we got a white PPT again. And so the CCS from part 2 contains the, actually, there are 2 ways we could show this. We could show it in the way I did it using Le Chatelier's. Let's do it that way. And so we'll look at this equilibrium here. Silver chloride plus 2 NH3s yields the Ag NH32 plus ion and chloride. And so what we could do is we could just say that, well, the H plus from nitric acid will attack this and generate ammonium, which is going to result in a shift left. Le Chatelier's shift left. Okay, that's another way. And later on we'll see it. Later on we're going to see this as a 2 equilibrium, and then in chapter 18. So this type of stuff we'll just write like this for now. And then in chapter 18 we're going to write it a little differently. Okay, so if you go through all these, then we test positive for silver. And so what would happen? What would happen if you're adding nitric and nothing ever precipitated out here? You're waiting and waiting and waiting and nothing precipitated out.
The absence of silver.
So does a negative prove the absence? I didn't get this last step, so that's. Does a negative prove the absence?
No. Why not?
No. Okay, yeah, it doesn't necessarily prove. I mean, if a negative, clearly, if you didn't get maybe any precipitate here in step 1, then that negative means a different thing than this negative at the end. You know, this negative at the end might just mean you added way too much ammonia, and that ammonia has to be killed off by the acid, and pretty soon things get too dilute, and you know, so negative can mean different things. So we have to be careful that, of how we interpret. And so understanding the chemical reactions here will give you a better insight into how to analyze and interpret your actual observations. We could take a look, since I'm not going to talk for very long, we could take a look at the next ion. What was the next ion that you tested for?
Well, 3 of them.
We'll write it over
Iron,
here.
aluminum, and chromium.
Iron, aluminum, and chromium. So let's just start with iron. Was it iron 2 or iron 3?
Iron 3.
It's iron 3 plus.
Aluminum 3 and chromium.
Yeah, okay, aluminum 3, but what we're going to do is we're just going to focus on iron because that was separated in a different branch. And so what we do is we look at what types of chemical properties does iron have. And so here are some of the chemical properties of silver: metathesis, Lewis acid base, or a reaction. For iron 3, the observation is this. We start off in the same thing. If we take our unknown aqueous and add HCl, what should we get with iron 3? This is a test for iron. It's a soluble salt, so we get NR. Well, a lot of people say NR, that's not important because we just want the reactions, but you know, having no reaction here is important because that's a chemical property of iron 3. It's not going to react with HCl, right? And so here, you know, there's no driving force. So when we look at the equation, we'll call this 1 for iron. So iron 3 plus HCl yields NR. Nothing's going to happen. Okay, then what's the next thing you did to this? You added ammonia or sodium hydroxide? Sodium hydroxide? Okay, so what we do is we take the solution. And so this is going to be the solution from 1 and add sodium hydroxide. And then what did you get? Well, this should result in a
Clear.
well, it's going to neutralize the acid, but we keep adding it until we get a precipitate. Yeah. What color is iron 3 hydroxide? Yeah, we should get a brown precipitate. Sometimes it's hard to see because it's mixed with other colors, right? And then that's the observation. The equation for this is going to be what? We have the brown precipitate of iron 3 hydroxide, solid, and then we, oops, no, that's the product. We have iron 3 ions reacting with hydroxide ions to form iron 3 hydroxide, solid. Oh, is it ammonia?
Yeah, because the magnesium ion will be.
Oh, right. Yeah, you know, this is a critical step. You know, here they didn't use sodium hydroxide. You know why they didn't use sodium hydroxide? They didn't use sodium hydroxide because they wanted to do what's called a selective precipitation. And the selective precipitation is we're just precipitating out the 3+ cations. In order to precipitate the 3+ cations, we don't need as much hydroxide. If you dump in a lot of hydroxide like this, you have the potential of precipitating out the 2+ cations as well. And so what we have to do is we have to do controlled precipitation in which the pH does not climb too high. If the pH, in fact, to precipitate out magnesium ion requires pHs in the 9s, you know, maybe the high 9 range. As long as we can keep the pH below 9, how can we keep the pH lower than 9, but above 7? We use a buffer solution. And we try to buffer it so the pH can't climb too high, and we buffer it by adding ammonium chloride. And so this is a more trickier reaction because really the observation here is it's the solution 1 plus ammonia, ammonium. And the purpose of this is a buffer. And the buffer is going to try to maintain a hydroxide, above 7 but below 9. And that way we can just precipitate out the 3+ cations. This is going to yield our brown PPT. Now the reaction for this is this. The way we think, what generates the hydroxide in this buffer? The Kb for ammonia or the Ka for ammonium? The Kb for ammonia. And so in this particular reaction, we're going to just ignore the ammonium because that's just lowering the hydroxide, and just go iron 3+ plus 3 hydroxide. Oh, no, that's still wrong, sorry. Iron 3+ plus 3 ammonias plus 3 waters yields iron 3 hydroxide plus 3 ammoniums.
Wait. It's not the buffer that precipitates out, right? It is sodium hydroxide.
No, there's no sodium hydroxide. It is hydroxide that precipitates it out. By having a higher pH, we're going to have hydroxide present, and that hydroxide will precipitate it out. Although the more ammonium we add, the less hydroxide we're going to have. The more ammonium we add, it's going to push it this way. And so it doesn't make sense to add ammonium here because we're going to not get as much precipitate due to the common ion effect, right? And so that doesn't make sense. So we're going to end up sacrificing a little bit, of iron 3 hydroxide in order to prevent the precipitation of magnesium hydroxide. Okay, what's the next step in the iron analysis?
Now we sodium hydroxide and hydrogen.
Okay, we add sodium hydroxide and hydrogen peroxide to this. Which one first?
Sodium hydroxide.
Sodium hydroxide?
10 drops.
10 drops. Okay. And so what we have here is a 4. Now, why are we adding now sodium hydroxide? Well, now we're adding it because we've separated out the other ions here. So now we just have the 3+ ions, correct? And so we don't have to worry about excess hydroxide now. We don't have to worry about excess hydroxide now because the magnesium isn't going to be there to precipitate out, and that would yield a white PPT. Okay, but what happens with the iron 3 hydroxide and excess sodium hydroxide? This you could just look at the flow chart and tell me.
Dissolve.
The PPT dissolves?
When you put it in hydroxide?
Yes. The iron 3 hydroxide. Just look at the next box and tell me what happened to the iron 3 hydroxide. It dissolved? Well, something dissolved, but not iron 3 hydroxide, right? The purpose of the excess hydroxide is not to attack iron 3 hydroxide. The purpose of the excess hydroxide was to attack aluminum, because aluminum is susceptible to attack by hydroxide to form, what's that called? Yeah, what's the complex's name? Not hexa, should be tetra hydroxo aluminate ion. Whereas iron, does iron form a tetra hydroxo ferrate ion? Does iron form a tetrahydroxoferrate ion? Why? Why does aluminum get attacked by excess hydroxide but iron does not? What kind of reaction is that when aluminum gets attacked by excess hydroxide? Is that a metathesis, acid base, or Lewis acid base? It's a Lewis acid base reaction. So that means hydroxide is a good Lewis base, so why doesn't hydroxide also attack aluminum? Iron. Iron's a 3+, aluminum's a 3+. Do you see why, this is the point I was trying to make earlier. The point I was trying to make earlier is, do you see why, for example, if you had sodium hydroxide will attack hydrochloric, but it won't attract nitric. Does that make any sense? Does that make any sense? If you have sodium hydroxide, will it neutralize hydrochloric? Yes. Will it neutralize nitric? Yes. Will it neutralize any acid? Any Bronsted acid? Yes. Right? Because Bronsted acids are proton donors, hydroxide is a proton acceptor. Well, you have a Lewis acid. The Lewis acid is iron 3, the Lewis acid is aluminum 3. Why does hydroxyl attack aluminum, but it does not attack the iron? Explain that to me. Why doesn't hydroxyl attack chromium 3? Was chromium 3 attacked? No. Right? And so the point of this is to explain that, you know, why is hydroxyl, which is a good Lewis base, so discriminating? Whereas as a Bronsted base, it's totally indiscriminate. It'll attack any Bronsted acid. Well, all Bronsted acids share one thing. All Bronsted acids have hydrogen as the electron pair acceptor, right? You could sit here. They have hydrogen as the electron. And so the acid parts are the exact same, but you would think iron 3, aluminum 3, chromium 3, they're all the same, aren't they? No, they aren't all the same, and it gets much more complicated. And so for predicting Lewis base strength, is it something that's easy to do? No. In fact, if you just look at electrical interactions, you know, +3, +3, +3, and -1, -1, -1, it doesn't make sense at all. So there's got to be more to Lewis acid base reactions than meets the eye. And what's the more to it than meets the eye?
It's the MO configuration.
Right. We are forming these coordinate covalent bonds, and so there's got to be something in that bond formation that. Now we aren't going to get into it, but you should realize that, you know, it's not just a simple chart. You know, iron 3 is a stronger Lewis acid than aluminum 3, or aluminum 3 is a stronger Lewis acid. No, it's more complex than that. Okay. But anyway, we expect no reaction here. And would that have been easy to predict? No, that's very difficult to predict. You know, at this point, we don't have enough theory to make that kind of prediction. At this point, it's just strictly observation. This is it. You know, a lot of people say, I hate memorization, but, you know, how are you going to predict this? You know, without looking at a chart or, you know, knowing it, you know? How are you going to predict this theoretically? I'd like to see it. Well, the equation here is, oops, I didn't want, this was supposed to be the observation. I ended up writing the equation. The observation is the brown PPT plus excess hydroxide, sodium hydroxide, yields NR. PPT shouldn't be touched. Now that's a chemical property of iron 3 hydroxide. And so the equation is here for 4. Then for 5, what did we do next? We added hydrogen peroxide. Did anything happen to the iron 3 hydroxide with hydrogen peroxide? No, because you know what? Iron 3 is... So we took the brown PPT, or did we do it? Yeah, we subjected this, right? Brown PPT plus hydrogen peroxide yields no reaction. In fact, iron 3, have you heard of iron 4? No. Hydrogen peroxide, what is that? It's an oxidizing agent, so would it oxidize iron 3 to iron 4? No. And so we have iron 3 hydroxide, solid, plus hydrogen peroxide yields NR, like we'd expect. The purpose of the hydrogen peroxide isn't for iron 3, but you know it's important because this is a chemical property of iron 3, right? It's already maxed out its oxidation state. What was the purpose of the hydrogen peroxide? Yeah, it was to convert chromium 3 to chromium 6. Yeah. Okay, what's the next step here? What was the next step? We dissolve the... Okay, so the brown PPT, this is from 3. The brown PPT, well, I forgot to write the numbers. So the brown PPT from 5 plus sodium hydroxide, or not sodium, we can't dissolve in sodium, well, in HCl, yields a solution, right? It should be a clear, did you see any color to it? Clear yellow solution, CYS. And so this iron 3 hydroxide here, solid, plus 3 HCl's is going to yield FeCl3 plus 3 H2O's.
Professor, what kind of brown are we supposed to get? Because when we did it, we didn't get it.
You don't have to get brown. It could be just faint.
Yellow.
Yeah. Color is very deceptive. You know what geologists do for color? You know, it depends on the size of the crystal. That changes the color. You know what color is silver? Silver. But do you know when the crystals of silver are very small, do you know what color it is? Black. Silver is black when the crystals are tiny. And so what geologists do is they get a plate and they try to scratch it and break minerals and rocks to see what color they are by making a fine powder. When they make a fine powder, then they look at the color. And so and they try to get the same consistency so they always get the same color, you know. And so depending on how big the crystals are. Well, the same thing, solutions, you know, the color, it also depends on the contaminants in there as well. And so color is very deceptive, and color throws people off, especially with their unknown, because the unknown contains a different mix of ions, so you get slightly different colors in everything. Well, not everything, but a lot of things, you know, depending on what mix of ions you have.
But the final product should be the color.
The final product should be a light brown color. Maybe a slightly rust color, PPT. The colors, you can always see what the reference color is because we have all the standard solutions there. I just grab a test tube, put a couple of drops of iron 3 chloride in, and then add some sodium hydroxide, and see what the color is.
It says that it's supposed to be a blue PPT. That would show that
Not yet. Almost. Almost. What's the next step? Yeah, we're going to add that. Potassium hexacyanoferrate. We're going to make this this thing called Prussian blue, which is isn't it Prussian blue they use on blue jeans or something like that? So we're going to take solution from 6 and then add potassium hexacyanoferrate 2. Okay, so hexacyanoferrate 2. So this means we have 4 potassiums?
Yes.
AQ. Was it an aqueous solution or was it solid you added?
It's a
Solution. And we got a blue
You should get a blue PPT.
PPT. A blue solution doesn't cut it because we're adding a blue solution. It's got to be a blue PPT. I think, is it a blue solution? I don't know. What color is potassium hexacyanoferrate? It's yellow. And so will a blue solution confirm it?
Yeah.
No, you have to see if
Or is it supposed to be a...
It's blue. The solution's blue.
the solution's blue.
It's not yellow. It's blue.
Okay, is there a PPT?
There is.
Okay. Well, you guys figure this out. So what is the reaction here? We got iron 3 plus the hexocyano. Wow, cyanide. Cyanide is pretty toxic, right? But this cyanide's a little different because this cyanide is covalently bound to iron 3 and it forms quite a stable complex here with a charge of 4 minus. And so we've just got to balance this out. We need 3 of the hexocyanos and 4 irons. Okay? What kind of reaction is this? Metathesis. All right, and so if we go through all these steps, then now we can say we tested positive for iron 3 plus. Negative tests mean it's either below the detection limit or you might have made a mistake. Or it might not be there. You know?
So in the cases below, do we add a little bit more of?
Yeah, we always add a little bit more to make sure. You know, the quantities are always adjusted. You know, for example, here, let's say you didn't have any silver ion, you're going to have a huge amount of HCl that has to be neutralized. So the amount of sodium hydroxide you end up, or ammonia you end up adding is enormous. In fact, if you're adding way too much ammonia to get the pH back to 7 or around 7, then I wouldn't do that. I would probably add a drop of sodium hydroxide to help, and then add the ammonia. You know, like say your pH is close down to 0, you know, then you might want to do that because people keep adding ammonia, and pretty soon it overflows. They pour it into another test tube or beaker, add more ammonia, because you know, they wanted to make sure that there was no silver chloride, so they kept adding HCl until they were absolutely sure nothing was going to precipitate. Do you see? And so we're always constantly making adjustments to do this. And so you look, well, in order to do this precipitation, this is what's required. All right, so, you know, I don't want to talk too long, so I'll stop here. And maybe, yeah, we'll just start working. And,